Hi, today's lesson is about the quantum mechanical model of the atom. A friendly reminder that it's Schrödinger who is given credit with coming up with this model, and he did a lot of math to prove the probability of finding an electron. In the electron cloud. So again, Schrödinger did a lot of math, and we watched a video where all the mathematical equations gave these different shapes to what the region of space where the electron would most likely be found would look like, and we're going to elaborate on them in a moment. So looking at the diagram here, all of these little dots are not meant to represent individual electrons, but rather the denser regions where the dots are closer together, that's a region where it's more likely or more probable that your electron will be found, which makes sense because it's going to be somewhat attracted to the nucleus. And the farther away you get from the nucleus, the chances of finding an electron there decrease. So this is an electron probability model. Now, when we try to explain where to find an electron in the electron cloud, there are some principles of Bohr's model that come into play as well. And those would be the energy levels. So here's the first explanation that Schrödinger gives us, and I'll number it 1, energy levels, as to where we'll find an electron in the electron cloud. These are like the rings in the Bohr model of the atom. So for example, we would have drawn the nucleus in the middle, and then we would have drawn concentric circles around the nucleus. And remember, this is a two-dimensional model of a three-dimensional, I don't want to say being, but thing. In reality, though, what Schrödinger discovered is that the energy levels themselves are not equally spaced apart. They don't have equal amounts of energy between them. So reading the caption again, the energy levels in an atom are similar to the rungs of a ladder, but they get closer together as they get farther from the nucleus. In other words, because the electrons are not attracted to the positive charge of the nucleus, it doesn't require as much energy for them to go to the different energy levels. So again, we're talking about where we can find an electron in the electron cloud. The first place we're going to find them is in these energy levels. There are going to be 7 energy levels, and we represent them with whole numbers. They are represented by the numbers 1, 2, 3, 4, 5, 6, and 7. All right. The next explanation about where Schrödinger argues that we'll find an electron in the electron cloud is in what are called sublevels. So that's the second location, sublevels. Sublevels are going to be the shape of the cloud, shape of the electron cloud. Now, as you research images of this quantum mechanical model, they'll all eventually come back to looking like this. And I hope it makes sense in a little while. The atom is going to always look like a sphere at the end. All right. There are 4 possible shapes that are represented by letters. And they are the letters S, P, D, and F. S stands for sphere, because again, we're describing the shape of the cloud. The P is going to be described as a peanut shape, meaning in the shell. The D and the F get a little overlapping. People call the D sublevels daisies and the F sublevel flowers. Now you may be thinking to yourself, what? These are not the legitimate names. The legitimate names are sharp, principal, diffusion, and fundamental. But in an introductory chemistry class, we use the names sphere, peanut, daisy, and flowers to help you remember that the purpose of the sublevel is to tell us the shape of the electron cloud. Now, how do we know how many sublevels are in the energy levels? The number of sublevels in an energy level is equal to the value of the energy level. The number of sublevels in an energy level is equal to the value of the energy level. Energy level 1 will have 1 sublevel. The number of sublevels is equal to the value of the energy level. Energy level 1, 1 sublevel. Energy level 2 is going to have 2 sublevels. Energy level 3 is going to have 3 sublevels. Etc. How do we know which letters? Well, let's think about it for a second. Nature likes things that are low in energy. Right? It's really easy to keep your room messy. It requires energy to keep it neat. It's really easy not to do your homework. It takes energy to have the discipline to do the homework. So nature naturally likes things that take less energy. So let's think about these shapes. A sphere looks like a baseball or a beach ball. The peanut in the shell kind of looks like a dumbbell shape. And then daisies and flowers. If I handed you a jar of Play-Doh, which of these shapes do you think would require the least amount of energy to make? You're right, the sphere shape. So the sphere shape is going to be made first. Followed by peanuts, followed by daisies, followed by flowers. The key here is that the sphere is made first. So when you look at energy level 1, it's only going to have one sublevel. The sublevel choices are S, P, D, and F. Which one will be in energy level 1? You're right, the sphere. Energy level 2 will have two sublevels. The choices for sublevels are S, P, D, and F. Which one will nature make first? You're right, the sphere. So we have energy level 2, sublevel S. But we now need a second sublevel. What will nature make after the sphere? The peanut. So we'll write energy level 2, P sublevel. We said before that energy level 3 will have three sublevels. The choices for sublevels are S, P, D, and F. Which one will nature make first? Yep, the sphere. The sphere is always made first. So we have energy level 3, sublevel S, and sublevel S is followed by P, then D, then F. So after 3S, energy level 3 will have sublevel P, and because we need to have three sublevels, it'll also have sublevel D. Let's keep going with the pattern. Energy level 4 will have four sublevels. Sphere, peanut, daisy, and the flower. Energy level 5 will have five sublevels. S, P, D, F. There are only four sublevels. Even though theoretically energy level 5 can have five sublevels, a fifth one doesn't exist yet. So we just stop after these four sublevels are created. Energy level 6 theoretically has six sublevels, but only four exist. S, P, D, F. And our final energy level, right? Energy levels, we said they're represented by the numbers 1, 2, 3, 4, 5, 6, and 7. Energy level 7 should theoretically have seven sublevels, but only four exist. S, P, D, and F. Before we move on, let's just regroup here. It's not an easy concept. We are trying to talk about the probability of where we will find an electron in the electron cloud. Where will we find an electron? The first place we'll find it is in an energy level. These are the rings around the atom in the Bohr model. They are represented by the whole numbers 1, 2, 3, 4, 5, 6, 7. Even though the Bohr model represents them evenly spaced, kind of like the rungs on a ladder. In real life, they're not. There's more distance between the energy levels that are closer to the nucleus, and as you get further and further away, there's less energy difference between the energy levels. Now remember, we're talking about clouds. So the clouds themselves are going to have a shape to them, and that shape is called a sublevel. There are 4 sublevels, S, P, D, and F, and the number of sublevels in an energy level is equal to the value of the energy level. Now these shapes of the clouds, again, it's a 2-dimensional concept on paper here, but we are talking about a 3-dimensional universe in which we live. So these clouds or these shapes or these sublevels can be arranged in 3-dimensional space in a variety of ways. The number of ways that they're able to be arranged is the 3rd part of Schrödinger's description about where we'll find an electron in the electron cloud. They are called orbitals. And an orbital tells us the number of ways the sublevels, and remember the sublevels are the shapes of the cloud, can be arranged in 3-dimensional space. Orbitals are the number of ways the sublevels, which are the shapes of the cloud, can be arranged in 3-dimensional space. Let's look at our simplest sublevel, the S sublevel. As you look at this sphere shape, if I were to look at it along the y-axis, try this. Oh, whoopsie daisies. If I were to look at this along the y-axis, it would, look like a bulge. If I were to look down on it from the z-axis, it would look like a bulge. If I were to look at it from the x-axis, it would look like a bulge. In other words, no matter what way I look at a sphere in 3-dimensional space, it's going to look identical along all of the axes. Therefore, there is only one way that the S sublevel can be arranged in 3-dimensional space. So the S sublevel will have one dash that follows it, and this is how we represent the orbital. Let's make that our next bullet. They're represented by dashes. Oh no, underscores, excuse me. After the sublevel. Let's try to put this together with some things we spoke about earlier. We had said that energy level 1, energy level 2, energy level 3, energy level 4, 5, 6, 7, they all have this sphere shape or this sphere-shaped cloud. How are they different from each other? It has to do with their size. And this is where we get those rings around the nucleus. So when you look at this first set here, the 1s cloud is smaller than the 2s cloud, which is smaller than the 3s cloud. Linking it up with the probability model, there are going to be areas in which the probability of finding an electron is 0. That's what's meant by these nodes. So as you look at this electron cloud model, again, remember this is two-dimensional. It should be three-dimensional. We've got it poking out at us too. So by the time you get to this 3S, all you see is like the yellow sphere, but underneath it or enclosed in it is the blue layer and the yellow layer for the 1S. So these clouds or these shapes, they get bigger as they layer on each other, sort of like those dolls that have the Manushka dolls, I think they're called, where you can, the largest one opens it up and then there's a smaller one inside and a smaller and smaller. That's the idea behind this. Let's look at our P sublevel. The P sublevel is our peanut shape. If I were to look at the peanut shape, let's look at this first one here in the upper left. If I were to look at it along the y-axis, I would see these two nodes. If I were to look at it either up or down on the z-axis, again, I would see two nodes. However, if I were to look at it along the x-axis, it would look bulgy, like the sphere does. So the P sublevel can be arranged 3 different ways in space. The P sublevel has 3 arrangements. These arrangements are called orbitals. So we represent that by underscores that come after the sublevel, and I will do 3 of them for the arrangement of the x-axis, the y-axis, and the z-axis. Now remember, these are all clouds and they all have origins. So if these 3 P sublevels were all layered on top of each other, it still sort of gives you this cloud or this spherical nature to it. Again, areas where there definitely won't be any chances of finding an electron. Let's look now at the D or the daisy. Notice how the shapes start to get far more complicated, and it's really tough to talk about them. So ultimately, we're going to count. There's 1, 2, 3, 4, 5 different ways that the D sublevel can be arranged in 3-dimensional space. Therefore, there are 5 D orbitals. How do we represent that? Underscores. So D will have 5 underscores after it. And then finally, the F sublevel, holy smoke, there are 1, 2, 3, 4, 5, 6, 7 different shapes proved mathematically by Schrödinger that the electron could most likely be found in. So the F sublevel has 7 orbitals. Coming full circle, we had said at the start of this explanation, this lecture, that we are talking about where we can find an electron in the electron cloud. Biggest picture is in the energy level. Next zone, it's in a sublevel or a specific shape of the cloud. Even more specifically, we can say which shape of the cloud the electron is most likely to be. And that is our final note. The electrons are found here in the orbitals. And we are going to represent them being electrons. Represent the electrons. using arrows. Let's come back together as a whole class to work through making sense of this organization system, moving through examples on the periodic table of the elements. Thanks for watching.